Let's take a look at what this problem's asking. There's a spider that's suspended from a tree branch by a piece of silk. Okay, now you tap the branch and send a vibration down the thread, down that piece of silk. And the question is this: how long does it take to reach the spider? So we're looking for a time interval. And the time interval that we're looking for is how much time it takes a vibration to travel down a thread. So this is basically a problem about a wave on a stretched string. So it's an appropriate one for chapter 15. Now let's go ahead and do some preparation, okay? First off, let's draw a picture of the situation. We have a branch here, and there's a length of spider silk, and at the end of the spider silk, there's a spider, okay? And let's just say the spider silk has a length L. We'll just use the symbol for it right now. The time that it's going to take the vibration to travel from here down to here, well, that's basically a kinematics problem, okay? It's just equal to the length divided by the speed at which the wave travels. And so ultimately, this question hinges on a calculation of the speed. Well, the speed is the speed of a wave on a stretched cord, and we know that's just equal to the square root of t over mu. Okay, now mu is the mass per unit length of the spider silk. Now let's take a look at this piece of spider silk here. You don't think about it, but you think it's just a thin thread. But really, if you think about it up close and personal, it's a cylinder. And the volume of a cylinder is the cross-section area at the end times the length, okay? So it's pi r squared times L. And so the mass of this particular piece of spider silk is equal to rho times v. It's just equal to the density times the volume. That's true for any object. And we know the volume is pi r squared times L. So the mass is equal to rho times pi r squared times L. And we have to compute the mass per unit length, m over L. Well, m is equal to rho times pi r squared times L, and if we divide that by L, the L cancels, and that makes sense because it's the mass per unit length, and so we don't expect it to depend upon the length. This is independent of how long the particular piece of spider silk is, okay? And that's just equal to rho times pi r squared. So we can compute the mass per unit length. The only other thing we need to compute the speed of the wave is the tension. Well, for the tension, let's do this. Let's do a free body diagram for the spider. So the spider's hanging from a thread. There's an upward tension force from the thread. There's a downward weight force. Now the net force in the spider is 0 because it's just suspended. So T is equal to W, but W is just equal to M times G. So we know the tension, we can compute the mass per unit length, we can compute the speed, and if we know that, we can compute the time for the wave to travel. And so we're ready for a solution. But before we do that, before we do a calculation, let's think about what our answer is likely to look like. So we'll do a little bit of pre-assessment. Now, spiders are very sensitive to vibration. They use vibrations of their silk to detect things in the world around them. So we expect the wave to travel pretty quickly. But we don't expect it to be much quicker than the speed of sound in air, okay? If the speed was significantly faster than the speed of sound in air, that would mean that the spider would have difficulty telling where a vibration was coming from, okay? So we expect it to be bigger than the speed of sound in air, but not too much bigger. And that's typical with the numbers we've seen in other problems in the chapter. The other thing is this: if it's that fast and it's only traveling 1.1 meters, we're going to expect the time to be pretty short. Well, let's go ahead and do our solution. Okay, first step in our solution is this. We're going to calculate the speed. That's equal to the square root of t divided by mu. Well, the tension is equal to m times g. It's just equal to mass times 9.8 meters per second squared. And the mass is 0.50 grams. Okay, so that's 0.50 times 10 to the minus third kilograms. Okay, it's given in grams, not kilograms, times 9.8 meters per second squared. And if we calculate that out, we get 0.0049 newtons. Okay? Next up, we can compute the mass per unit length. We can compute that quantity mu. Well, that's just equal to rho times pi times r squared. Now, we aren't given r. We're given d. Okay, it's 0.002 millimeters, the diameter. So the radius is half of that. It's 0.0010 times 10 to the minus third meters. That's the radius. The density is given. It's 1,300 kilograms per cubic meter. So mu, if we calculate that out, comes out to be 4.08 times 10 to the negative ninth kilograms per meter. So that means 1 meter long piece of spider silk is going to have a mass of 4.08 times 10 to the minus ninth kilograms. And that makes sense. Spider silk is pretty diaphanous, and so we expect this to be a tiny, tiny mass. So that number makes sense. And the tension is small because the spider's mass is pretty small. When we compute the speed, we have the ratio of a tiny number divided by an even tinier number. And so we're going to get a number that is reasonably big. When we compute this, okay, we'll take these numbers, compute the speed, and we get 1,095 meters per second. Now notice, this is an intermediate stage in the calculation, and so I'm keeping extra digits, okay? Ultimately, this is a two significant figure problem, and so we'll round to two significant figures, but for now, we'll keep this. So the time interval, okay, is just equal to the length that the pulse has to travel divided by the speed of the pulse, which is 1,095 meters per second. The length is 1.1 meters, and so we end up with a time interval of 1.0 times 10 to the minus third seconds, or 1.0 milliseconds. Now this speed is reasonable based on what we saw previously, or based on what we said we would expect. And so the time is very, very short, and we expect that to be true. The spider lives and dies by its ability to sense vibrations, and so it needs to be able to sense them quickly. And so ultimately, our answer matches our expectations for how the world works.